Welcome to the presentation of our Group A. Today, we will walk you through three chapters. It's chapter 4, chapter 6, and chapter 7. First of all, let's go to chapter 4 together, which is the substitute and complementary commodities. So first of all, what is substitute commodities? They are the good that can replace each other in the consumption. So as you can see on the graph here, so the x-axis is the demand of the tea, and the y-axis is the price of coffee. So when the price of coffee increases, then the quantity demanded of tea also increases too. So the things that we need to remember for the substitute commodity is that when the price of A increase, the demand for B also increases, then that is the characteristic of the substitute commodity. For the complementary commodities, it is different. Uh, these are the goods that are used together. So when the price of the product A increase, the demand for B no longer increase. Now they decreases. Price A increase, demand for B decreases. So as you can see on the graph here, I take the example of butter and bread because these two goods are commonly used together. So the x-axis is the demand of bread and the y-axis is the price of butter. So when the price of butter increase, then the demand of bread is decreases because they are these products are usually consumed together. So when the other product the price is get too expensive, then demand for other product is decreases. The demand of bread is depend on the price of butter. Okay, so if we have two products with different prices and we want to analyze whether the changes in the price of one of the product affect the demand for the other or not, and if it does affect, then how can we tell that which type of relationship are they, substitute or complementary? So we have the two methods that we can help us to identify it. First of all is partial derivatives. Okay, so suppose we have the quantity demanded function for product A and product B, as you can see in this, and PA and PB is the respective prices for product A and product B. So based on this demand function, we can find the four different partial derivatives. The first one is the marginal demand for product A with respect to the price of product A. Okay, and the derivatives number two is different. We still find the marginal demand for product A, but now with respect to the price of product B, and the marginal demand for product B is the same with A. Okay, so if those products are substitute, then there are two requirements that we need to satisfy. The first one is that the marginal demand of product A with respect to price B must greater than zero, and the marginal demand of quantity product B with respect to the price A must equal to must greater than zero. So if these two requirements are satisfied, then we can conclude that these two products are substitute. If just only one of them are satisfied, then we cannot conclude they are substitute. Okay. For complementary commodities, if the marginal demand of product A with respect to the price B lesser than zero, and the marginal demand of product B with respect to the price A lesser than zero too, then we can conclude these two products are complementary.
Let's break down some examples for further understanding how to identify substitute and complementary commodities. So the first example, suppose that there are two demand equations for related products A and B, where could A and could B or the number of units of A and B demanded when the unit prices in thousands of dollars or PA and PP respectively. So let's classify A and B as competitive, complementary, or neither. So first, let derivative of these two demand functions to measure how the quantity of one good changes when the price of the other good changes. As the result illustrated in the slide, both the derivative are negative, which means that they are complementary commodities. In economic terms, this means that an increase in the price of one good will lead to the decrease of demand in the other goods. A classic example is between sugar and coffee. When the price of coffee rising, people may drink less coffee, which leads to the decrease in sugar consumption. Moving to the next example, just like the previous one, here we need to compute the partial derivative of these two demand functions to classify A and B product as competitive, complementary, or neither commodities. So let's compute the partial derivative of these two demand functions. The first one, the marginal product A respect to the price of B is 3, which means that when the price of product B increases, the demand for product A also increases. However, the marginal product B with respect to the price A is negative 3, which means that when the price of good A increases, the demand for product B will decrease. In other words, these two derivatives are opposite signed number, which means that A and B are neither supplementary nor complementary commodities.
Now, let's move on to the second method, which is the cross-price elasticity of demand. So we just only need to focus on the formula in the third in the third row, okay? Which is like the price of product B divided quantity A multiple the partial derivatives. Okay. So with that formula, how can we tell that whether the goods are substitute or complementary or not based on the cross price elasticity of demand? So if the goods are substitute, then the partial derivatives is greater than zero, right? And then it will make the cross price elasticity of demand greater than zero. Why can we say that? Because the price of product B divided quantity demanded for product A always greater than zero. Price cannot be negative, and also the quantity cannot be negative. So the first part is always positive. So when we multiple the partial derivative, which are positive because these goods are substitute, then it will lead to the cross price elasticity is greater than zero. But if the goods are complementary, the partial derivative now is lesser than zero. We have just discussed before in the previous slide. So then it will make the cross price elasticity of demand positive, multiple the negative, we have the negative part. So the result is negative. Okay. So now I will give you the exercise for you can use that formula. Yes. Okay, now the demand function for T is this function, and we give you the values of the price T, which is 20, and the price for coffee is 30. Okay, now calculate the cross of demand, whether T is a substitute or complementary commodity. So step one, we need to calculate the quantity demanded of T using the given value I just showed you. Okay, and which is 300 minus 4 multiple 20 plus 3 multiple 30, and the final result is 310. Step 2, we find the partial derivative. Now is the marginal demand of quantity demanded for tea with respect with the price of coffee, because we want to analyze that whether the change in the pricing has any effect on the quantity demanded of tea. Okay, so because this partial derivative, we use the respect with the price of coffee. So 300 and the part minus 4 pt, we can delete it because it is the constant value. So we have the remaining part, which is 3 multiple price of coffee. Because this derivative, so the remaining part is only 3. So the partial derivative for the quantity demanded of T with respect to the price C is equal to 3. Now we calculate the cross price elasticity of demand. Okay, so we use this formula. So price of coffee we have before is 30, and quantity demanded of T, which is we can use the result from the step 1 is 310. We multiply the partial derivative that we have just found in step 2, which is 3, and we multiply these two, and the final result is 0.29, which is greater than 0. Because the cross price elasticity is greater than 0, then the tea and coffee are substituted, meaning that the increase in the price of coffee will lead to an increase in demand for tea. Specifically, is that now people will buy more tea if the price of coffee is just getting more expensive.
Hi, I'm Nguyên, and now I will discuss chapter 6 with about relative input and output models. For your information, the father of input and output model is Wassily Leontief. In the 1930s, to model the economic system, Wassily Leontief applied the matrices, which were then referred to as the input and output models. According to Dr. Wayland and in 2018, Leontief's input-output model describes a simplified view of an economy, and its goal is to forecast the proper level of production for each of several types of goods and services. To be specific, for the economy to operate properly, there are two fundamental requirements for the proper level of production to meet. Chief among these is that there ought to be enough of each good produced to meet the demand for it, whether it is for internal use within the economy or for external demand. Furthermore, Dr. Wayland also emphasized that there should be no leftovers or unusual goods. In other words, everything produced to be consumed and accounted for. Overall, there are three fundamental principles that this model is based on. The first one is the interdependence of sectors. For instance, assuming that the economy consists of only three main sectors, the manufacturing, the agriculture, and the utilities. In this model, it can be observed that the manufacturing sector depends on agriculture, since these industries require food to sustain their workforce. Additionally, the manufacturing sector relies on the utilities sector for electricity and water, which are essential for operating machinery and equipment. Similarly, the utility sector, which supplies energy sources such as electricity and water, relies on agriculture for food to feed its workers and on manufacturing for the machinery needed to support its operation, and the same interdependence also applies to agriculture. The second principle is that the total inputs, which are also known as the goods and services consumed by industries, must be equal to the total outputs of the goods and services produced by those industries. And finally, the third principle is the matrix representation. To be specific, when conducting a table describing the relationship between sectors, each of the rows would correspond to a particular sector, and it shows where the sector gets its input from. Similarly, each column would also represent one specific sector and demonstrate where that sector outputs go to, and this entire model could be transcribed into a matrix where how changes in one sector affect others can be observed and analyzed. For example, after observing this table, we can conduct the consumption matrix A and the external demand matrix D respectively as follows. And moreover, to read the consumption matrix properly, it is important to remember that Aij would represent the amount of inputs from industry J needed to produce 1 unit of output in industry I. In this case, if A12 equals 0.25, then it means that to produce 1 unit of output, the manufacturing needs 0.25 units of output from the agriculture sector. To find the production matrix S, it is important to take into consideration that the production matrix must not only be able to supply the market demand, but also need to consider their own internal consumption. Hence, we have the following model, where S equals AS plus D or S minus AS equals D, and this can be simplified by I minus A times S equals D, where I is the identity matrix, I minus A is the Leontief matrix, and the whole equation is also known as the Leontief equation. And finally, S is found by this red equation, where S equals I minus A powers minus 1 times D.
And to continue, we will examine a simplified example of Leontief's input-output model. As previously explained, this slide presents a three-sector economy: manufacturing, agriculture, and utilities. The table on the left, matrix A, shows the direct input coefficients, indicating the input requirements for a sector to produce $1 worth of output. The table on the right, matrix D, represents the external demand for each sector's output, and our goal is to find the total output that each sector needs to produce, denoted as X, and to satisfy both the input demands of other sectors, the A relationships, and the final demand from the market, D. To do this, we will move to the next slide and examine the calculation steps. This slide shows the steps to find the production matrix X. We already know matrix A is the direct input coefficients matrix, and matrix D is the final demand matrix from the previous slide. And matrix I here is the identity matrix. In the case, it's a 3 by 3 matrix with ones on demand diagonal and zeros elsewhere. And the next step is to compute matrix I minus A. Do this by subtracting its corresponding elements of matrix A from matrix I. For example, the element in row 1, column 1 of I minus A will be 1 minus 0.2 equals 0.8. Similarly, the element in row 1, column 2 will be 0 minus 0.25 equals negative 0.25, and so on for our elements. The result is the matrix I minus A, as you can see on the slide. And this matrix represents the net production requirement after accounting for internal consumption. And move on to the step 3. This is a more complex mathematical step. We need to find the inverse matrix of I minus A. The inverse matrix denoted as I minus A to the power of negative 1. And the result of the inverse calculation for the example is on the slide. As you can see, this matrix is called the Leontief inverse matrix. Each element of this matrix tells us the total amount of output from the sector in the row that is needed, both directly and indirectly, to satisfy one unit of final demand for the sector in the column. Moving to the last step, we have to compute the production matrix X. Finally, to find the production matrix X, we multiply the Leontief's inverse matrix I minus A to the power of negative 1 by the final demand matrix D. Matrix multiplication is done as follows. For the output needed for the manufacturing sector, is 1. We take the first row of I minus A to the power of negative 1, 1.3445, 0.3835, and 0.1870, and multiply it by the elements of D, 40, 50, and 60, and then add the result. X1 equal 1.3445 times 40 plus 0.3835 times 50 and plus 0.1870 times 60. Therefore, we will have X1 equal $83.80 billion. And for the output needed for the agriculture sector, X2, and output needed for the utility sector is 3. The calculation for x2 and x3 will follow a similar process, and therefore we will have x2 equals $74.23 billion and x3 equal $84.81 billion. So we have calculated the output needed for each sector. Therefore, we will have the manufacturing sectors needs to produce approximately $83.80 billion. The agriculture sector needs $74.23 billion, and the utilities sector needs $84.81 billion. And this is the final output level needed for each sector to meet both production needs and consumer demand in three sector economy.
And now I will talk about Chapter 7 with titles How to Solve Nonlinear Programming in Excel. Generally, linear programming is the mathematical optimization method that seeks to determine the best possible outcome for a given objective function. Constraints in the mathematical models. Besides, there are some applications in linear programming, including resource distribution, cost minimization, and profit maximization. Solving linear programming in Excel includes segment steps: formulating the problem, setting up the spreadsheet, defining the objective functions, defining constraints, using solver, and interpreting the results. The first step is to formulate the problem. Firstly, I need to identify decision variables, including number of products to be produced, and after defining the objective functions, maximize profits or minimize costs, and I will identify constraints, materials, labor, or budget. The second step is to set up the spreadsheet. I will create a spreadsheet with columns for decision variables, constraints, and coefficients. After that, defining formulas, multiplying resource usage per unit by decision variables, and using the objective function formula. The following step is to define the objective functions. In the spreadsheet, use a formula sum product to calculate the values of the objective function based on the decision variables. And after that, determine whether you want to maximize or minimize this differential. The next step is to define constraints. Write a formula calculating the left-hand side of the constraints, and then specify the constraint type and the right-hand side values. However, ensuring these values do not exceed their respective limits. Use solver is the following step. Firstly, I have to open solver, collecting data, analysis, and solver, and then set the objective cell whether to maximize or minimize, and the changing cell decision variables. After that, add constraints by clicking at and specific the constraint cell and inequality type. Clicking solve and accept the solution if feasible. The final step is to interpret the results. Review the optimal value for decision variables and the objective functions, and then analyze the constant to understand how the solution satisfies the problem's limitations, and use the answers and sensitivity reports to gain insights to the solution.
Let's go to the example for the chapter 7. So first of all, you have to check that if your Excel have a server or not, because we're gonna use the server on Excel to solve the linear programming. So if you click on data tab, you see the server, so you don't have to install. But if you don't have it, you're gonna choose the file options, click add-ins, Excel add-in, go, choose the server ID and go. Now I have two examples, one with two variables and the second one would be three variables. Now this row will maintain the coefficient of the objective. For each one we have 5, x2 is 7. Oh, this one have to be y. This one will be p. And this will be the answer for b. And you have to write down the equations. First one multiplied by this plus 7 multiplied by y. Enter. And do the same thing to the constraint. The constraint have 2, 3. After doing this, we will use the solver to solve it. So solver to this box will be the set objectives. Will be this one. Choose the mask for the maximize. Changing variables will be this two. Okay. And now do the constraint. Okay. Now, if you look at this, x and y have to equal or low or greater than 0, so it's gonna be non-negative. So now we will have the answer right here. Let's go to the second examples. We do the same as like the first one, but I'm gonna change a little bit. First, just write down the coefficient. Now, because the equations we have more changing variables, so I won't write down the equations. I'm gonna use sum product, comma, and enter. And now do the same. Comma. Now use server. We have the answer right here. So we're gonna use the result on the textbook to check it. And after checking it, we will see that those are correct. And this is the end for the exercise for chapter 7.
Here's your reference list. And that's the end of our group presentation. Thank you so much for listening.